Every year, over 130 million tons of glass are produced worldwide, a weight equivalent to 1.3 million Eiffel Towers. Imagine, mountains of broken glass, taller than skyscrapers, are transformed into crystal clarity thanks to fires of 3,000 degrees and laser snipers that knock out impurities at a rate of thousands of shots per minute. From ancient glassblowers who breathe life into red-hot bubbles, to futuristic tin baths where glass is born perfectly flat like a mirror. But behind this symphony of fire lies a secret. What if glass holds the secret to eternal reincarnation, which will allow us to turn the world upside down? Watch until the end, and you'll find out something you never imagined about this transparent, amazing material. Ready for the journey? Although the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in methods that give it character and uniqueness. This path from a simple transparent sheet to a work of decorative art is a fascinating journey. To create glass with individuality that carries the imprint of a human touch, masters still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at a temperature of 2,000 degrees Fahrenheit. He gathers a honey-like ball of molten glass on the end of the pipe, and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, glowing hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach a length of several feet. After the ends of the cylinder are cut off, it is cut lengthwise and placed back in the furnace. There, under the influence of heat, it slowly unrolls, like a scroll, and the masters smooth it into a flat sheet. Glass born in this way is never perfectly flat. It lives its own life, retaining barely noticeable waves, tiny air bubbles, and thin lines that tell the story of its fiery birth. This glass has a watery, organic quality that cannot be replicated by a machine. But the creation of unique glass does not stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing or sintering allows artists to literally paint with glass. Multicolored pieces of glass are laid out on a base sheet and sent to a furnace, where at a temperature of 1,500 degrees Fahrenheit, they merge into a single whole, creating bright, painting-like compositions. Closely related to this is the process of slumping or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold lying beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two sheets of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating complex patterns on its surface, from simple geometric shapes to photorealistic images. Thus, by combining ancient crafts with advanced technologies, modern production transforms simple glass into an expressive architectural material, capable of shaping light, color, and space. In the modern world, where tons of used glass containers are collected daily, the path from the trash can to a new bottle is not just remelting, but a high-tech odyssey, controlled by computers and light. Imagine a mountain of broken glass, reaching a height of tens of feet, where transparent, green, and brown fragments are mixed with labels, caps, and ceramic impurities. Turning this chaos into pure, raw material is a task for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, resembling a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull any steel impurities from the stream, and then eddy current systems literally shoot out aluminum caps and foil into separate containers. Powerful air currents blow away light paper labels and plastic remnants. But the most difficult task lies ahead, removing impurities that are almost indistinguishable from glass in weight and size, such as pieces of ceramics, stone, or porcelain. These enemies of glass do not melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to a high speed and fly through a scanning zone. For a fraction of a second, each fragment is illuminated by bright light, and high-speed cameras take hundreds of pictures. A computer system with lightning speed analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and gives a command to a battery of air nozzles. A precise, sniper-like stream of compressed air knocks the unwanted element out of the general stream, sending it to waste. This process is repeated thousands of times per minute. In parallel, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only transparent glass, knocking out all colored fragments with air jets, or separate the stream into 3 separate color fractions. As a result, at the output, a perfectly clean, color-sorted raw material is formed. Cull it, ready for a new life without loss of quality, which is the pinnacle of the modern circular economy. Then, flat glass can be made from this raw material. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that transforms ordinary raw materials into perfectly transparent sheets. It all begins in a huge melting furnace, the fiery heart of the factory that operates continuously for years. Into this furnace, resembling a lake of molten fire, a carefully dosed mixture, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stabilization. To this is added a significant amount of cullet, or crushed recycled glass, which helps to speed up the melting process. Inside the furnace, at infernal temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a homogeneous, viscous liquid. The melting process is strictly controlled to ensure the complete dissolution of all particles and the removal of gas bubbles, creating a flawlessly clean melt. From the furnace, this stream of red-hot to bright orange-colored glass, resembling a river of lava, smoothly flows into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet in length, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and does not mix with it, it spreads over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from below, and surface tension smooths it from above, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with an accuracy of a fraction of an inch. After forming a perfectly flat surface, the glass ribbon, still very hot but already solid enough to hold its shape, enters the most tranquil but critically important stage: annealing. It enters a long tunnel known as an annealing lehr. If the glass were cooled too quickly, its surface would contract faster than its interior, leading to the creation of huge internal stresses that would make it brittle and prone to cracking. In the lehr, however, the temperature of the glass is slowly and controllably reduced over several hundred feet, from over 1,000 degrees Fahrenheit to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the lehr emerges a single, flawless, continuous ribbon of completely transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Every year, only a few dozen combat machines capable of changing the course of a battle are produced worldwide. One such giant is born in the heart of the United States at the Boeing factory in Fort Worth, where every bolt, every weld seam is inspected with micron precision. Here, fuselages made from metal plates are joined into a single, strong body, and powerful T-700 engines and Hellfire missiles turn the machine into a formidable weapon. But there is one detail that only those who work behind the scenes of this production know. Watch until the end, and you will discover a secret that changes the perception of these helicopters forever. The main production facilities are located in the United States, particularly at the Boeing plants in Fort Worth, Texas, where the helicopter is manufactured using modern technologies. At these plants, the assembly of the helicopter's main components, such as the fuselage, rotors, and weapon systems, takes place. The production process includes automation to increase efficiency and accuracy, which is critically important for military equipment. An important part of the production capacity is also contracts with component suppliers. Orders for electronics, engines, control systems, and other parts come from various corners of the world. These suppliers must meet strict quality standards to ensure the reliability and combat readiness of the helicopter. In addition, the U.S. Department of Defense works closely with Boeing to control production, which allows for ensuring compliance with all specifications. This includes conducting regular inspections and tests at various stages of production to account for all potential problems. The production facilities engaged in the manufacturing of the AH-64 are also constantly improving their processes. With the introduction of new technologies and production management methods, such as lean manufacturing, the company strives to reduce costs and shorten production time without compromising quality. The main components, such as electronics, engines, navigation, and control systems, are manufactured in different countries. For example, the T-700 engines used in the AH-64 are produced by General Electric in the USA. Weapon systems, such as Hellfire missile launchers, are manufactured by many defense contractors, both in the US and outside the country. The electronic system, including radar and fire control systems, is supplied from various countries, such as Israel and the United Kingdom. This allows for the integration of innovative technologies that are constantly being improved in military aviation. The delivery of components to the Boeing production facilities in Fort Worth is carried out through various logistics channels. International transport is often carried out by air and sea, depending on the urgency and volume of the cargo. Key components can be delivered by express air transport to reduce manufacturing times. Upon arrival at the Boeing plants, the components undergo additional inspection to identify possible defects and non-conformities. After the delivery of all components to the Boeing production facilities, they arrive at the huge factory territory in Fort Worth, where several hangars are organized for helicopter assembly. Here, a primary inspection of each batch of parts is carried out. Specialists carefully inspect the components to identify any defects or non-conformities with standards, which ensures a high level of quality. The production process begins with the assembly of the fuselage, which is the helicopter's foundation. In this stage of work, huge metal panels, drawn out in the form of long and wide sheets, are used. The fuselage consists of several sections that are welded together to create a single, strong body. First, the workers coordinate all requirements and drawings, focusing on the accuracy of measurements. They carefully install the fuselage base on a special platform that allows easy access to all elements. In parallel with this, engineers ensure that each element meets strict quality standards. During the fuselage assembly process, workers use a variety of tools, from electric drills to specialized welding machines. Welding takes place far from any unpredictable movements, as this is critically important. Even the slightest inaccuracy can affect the helicopter's combat stability. The flame of the welding illuminates the workspace, adding a bit of heat to the surrounding environment. After the main parts of the fuselage are joined, it is checked for leaks. This includes leak testing liquid is pumped through special pipes to ensure that the body's reliability meets the requirements. Usually, workers suspect a problem if they hear a sound similar to a whistle or a pop, which could indicate issues. When the fuselage successfully passes all tests, it is time for painting. The application of coatings is important as it prevents corrosion and increases resistance to weather conditions. After painting, the fuselage is sanded to ensure a smooth surface, and then all parts are checked again to confirm they are installed correctly. After the fuselage assembly is complete, the next stage is the installation of the electronic systems, which play a critical role in the combat effectiveness of the AH-64. After the fuselage is prepared, it is moved to a special hangar where technicians begin to carefully install various electronic components. These systems control everything from navigation to the weapon control system. During this process, specialists install elements such as radar, which provide an overview of the battlefield, as well as fire control systems. These components are particularly sensitive, so it is important to adhere to huge accuracy. Workers use various tools, such as drills and screwdrivers, as well as specialized devices for laying wires. The next step is the installation of the engines. For the AH-64, T700 engines are used, which are powerful and reliable. After the engines are delivered to the factory, technicians check them for compliance with technical specifications. During the installation process, the engines are mounted on the fuselage, and all necessary systems, such as fuel supply and cooling, are connected. This process requires great attention to detail, as the engines must be securely fixed and correctly connected. After the installation of the engines and electronics, the stage of integrating the weapon systems begins. The helicopter is equipped with various armaments, such as Hellfire missiles and an M230 machine gun. In this stage, technicians use multi-step procedures to install and calibrate the systems. Each weapon unit is equipped with electronic systems that ensure its functionality. After installation, a check for the compatibility of all components is carried out. Having completed the integration stages, the fuselage proceeds to final assembly, where various systems are connected hydraulics, as well as control mechanisms. Hydraulics provide the helicopter's mobility, and its installation is a critically important task. Technicians check all connections for tightness, as a leak of hydraulic fluid can lead to serious problems during flight. During the testing of the AH-64, a real show of technical skill takes place. Aerodynamic checks are conducted in a large open area where the helicopter takes to the air, demonstrating breathtaking maneuvers. From a height, it performs turns, hovers in the air, and makes steep descents, showing its stability and ability to react quickly to the pilot's commands. Spectators can see how the powerful engines work at maximum revs, filling the air with their roar. On the ground stand, the atmosphere is also tense. Experts closely watch every movement of the helicopter, keeping an eye on the digital indicators on the monitors. The sounds of testing the electronic system, as the helicopter actively responds to control commands, are impressively complex. When the weapon system is launched and green indicators appear on the monitors, everyone present experiences a moment of elation. It's a sign that everything is working, and the helicopter is ready for combat missions. The team of engineers is gathered on the territory. They are dressed in special equipment and focused on their work. When the entire system passes the checks, a look of satisfaction appears on the experts' faces. Each of them knows that their work is bearing fruit, and the Ready for Real Flights helicopter will become an important element of military power. These tests provide not only an adrenaline rush, but also pride in the technologies that bring it to life. Every hour, over 4.5 million tires are discarded worldwide. But in Nigeria, a country with over 220 million people, old tires are not just trash. They are a currency for survival, an underground business, and even art. Here, worn-out rubber doesn't go to a landfill. It's taken apart, rolled on bicycles, cut by steel jaws, and baked into colorful tiles. How did poverty, ingenuity, and chemistry create a whole shadow industry? And what unexpected secret is hidden in one of the largest pyrolysis furnaces in Lagos? Watch until the end, and you'll see what they probably don't show in textbooks. Nigeria is the most populous country in Africa, home to over 220 million people. For many of them, a car is the primary means of transportation and doing business. Millions of passenger cars, minivans, trucks, and motorcycles travel the country's roads daily, inevitably wearing out their tires. The more vehicles, the larger the flow of used tires. The condition of roads in many regions of Nigeria is, to put it mildly, far from ideal. Numerous potholes, ruts, gravel surfaces instead of asphalt, and the general neglect of the road network lead to extremely rapid and aggressive tire wear. A tire that could last 40 or 50,000 miles in countries with high-quality roads might become unusable 2 or even 3 times faster in Nigerian conditions. A significant portion of cars in Nigeria are imported used vehicles, known as tokunbo. They often arrive from Europe, the United States, and Asia, with already significantly worn tires that require almost immediate replacement after purchase. This creates an immediate stream of old tires into the waste market. Due to economic hardships, many Nigerian drivers cannot afford expensive and high-quality tires from leading brands. They are forced to choose the cheapest options, either low-quality new tires, mainly from Asian countries, or already used tires. Both options have a very short service life, which creates a continuous cycle of buy, drive a little, throw away. Until recently, the country effectively had no established and efficient state system for collecting and recycling tires. Without proper disposal infrastructure, old tires simply accumulated in makeshift dumps, on roadsides, in vacant lots, and in water bodies, turning into a serious environmental threat. Only recently have entrepreneurs begun to see a business opportunity in this. The process of collecting tires in Nigeria is a fascinating, mostly informal, and multi-level system that operates not by government decree, but by the laws of the market and simple economic benefit. At the heart of the entire chain are thousands of individual collectors. These are often young men or people with low income, for whom collecting waste is their main livelihood. So, where do they collect them? The main source is tire shops and car repair workshops. Drivers leave old tires after a replacement. For the workshop owner, this is trash that needs to be disposed of. A collector pays him a small amount, or simply takes them for free. Collectors also literally patrol their neighborhoods, looking for abandoned tires in makeshift dumps and on roadsides. The tires are rolled by hand, transported on wheelbarrows, bicycles, or small 3-wheeled scooters. One old tire can cost from 50 to 200 naira. That's a few American cents, depending on its condition and size. It's not much, but by collecting several dozen a day, one can make a living. Collectors rarely deal directly with large factories. They sell their harvest to local middlemen. Middlemen are small entrepreneurs who own a small truck or pickup and a place for storage, usually just a fenced-off plot of land. They buy tires from dozens of street collectors. This is where the initial accumulation happens. They might collect several hundred or 1,000 tires before the batch becomes large enough for further sale. This is where those mountains of tires appear, but on a local scale. In the yard of such a middleman, you can see piles of tires that he accumulates, waiting for a good price or a sufficient volume for transport. Basic sorting might happen here. For example, separating truck tires from passenger car tires. The middlemen make their profit on volume. They buy cheap from collectors and sell for a higher price to large processors. Large recycling companies are at the top of the chain. Companies engaged in pyrolysis or the production of rubber crumb are the final buyers. These are recycling plants like Freetown Waste Management Recycle or large pyrolysis facilities. They make deals with the middleman. The aggregator loads a large truck of 5 or 10 tons and brings the tires directly to the plant. The plant accepts the raw material, weighs it, and pays the middleman by tonnage. This is where the final, professional sorting takes place. The tires are inspected, cleaned of dirt and foreign objects before being sent to a shredder or pyrolysis furnace. As soon as the tires arrive at the recycling site, they head down one of 2 main paths. The choice of path depends on the technologies the company possesses and the final product it wants to obtain. Pyrolysis is a method used by large industrial plants. The goal is to break down the tire into its basic chemical components to obtain industrial raw materials. Tires cannot be loaded into the reactor whole. First, they undergo tough preparation. Powerful hydraulic shears cut out the bead ring from the tire, a thick steel wire that ensures a tight fit on the rim. Then the tire is sent to an industrial shredder. The machine's steel jaws tear and cut the rubber into pieces a few inches in size, turning it into a uniform mass resembling coarse chips. The prepared rubber pieces are loaded into a sealed metal reactor. This is the heart of the entire process. The reactor is heated to high temperatures, 800 degrees Fahrenheit, but the key condition is a complete absence of oxygen. Because of this, the rubber doesn't burn. Instead, its long polymer molecules begin to break down into simpler substances. As a result of the heating, a mixture of 3 fractions is formed: a gaseous fraction, a liquid fraction, and a solid residue. After the cycle is complete, the factory obtains 3 products ready for sale. The first is pyrolysis oil, which is used as fuel for industrial furnaces and boilers. Carbon black is sold to manufacturers of paints, plastics, and new rubber products, and the steel wire is collected by magnets, pressed into briquettes, and sold as scrap metal. Another path for recycling old tires is mechanical recycling and upcycling. This path is chosen by companies like Free Recycle, which create finished consumer goods. There is no chemical reaction here, only physical transformation. The tires also go through shredders, but the goal here is to obtain clean rubber crumb of various sizes. During shredding, powerful magnets extract steel fibers from the rubber mass, and air separation systems blow out textile fibers. The output is clean rubber granules. The rubber crumb is poured into a large mixer. 2 key ingredients are added to it: polyurethane glue and pigments. The glue will bind the rubber particles together, and the pigments will give color to the future product. The resulting mixture is thoroughly mixed until uniform. The colored rubber mass is placed in metal molds of the desired configuration, for example, in the shape of paving tiles or mats. Next, the mold is sent under a hot press. High temperature and pressure activate the glue, baking the crumb into a single, durable, and elastic product. This can be bright and safe paving tiles for playgrounds, durable flooring for gyms or garages, soles for shoes, or even entire flip-flops. A separate direction is upcycling, where whole tires or their large pieces are turned into original furniture, such as tables or chairs and other decorative items. Thus, depending on the chosen path, an old, unwanted tire is transformed either into a valuable industrial raw material or a new useful household item. Every year, over 50,000 tons of uranium are mined worldwide. But to get just a few grams of energy from it, you have to move mountains. It all starts in the desert, where the temperature reaches 100 degrees and ends in a reactor that powers New York. Here, centrifuges that spin faster than an airplane turbine, and substances that corrode metal in seconds. But the most interesting part is what even safety instructions don't talk about. Watch until the end, and you'll discover a secret that will change your perception of nuclear energy. It all begins in the dust. And that's not figuratively speaking. Uranium ore is mined in hot regions: Arizona, Wyoming, Texas, New Mexico. Sort of like cowboy landscapes, only instead of lassos, there are drilling rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is scorching, up to 100 degrees Fahrenheit in the shade, if you can find any. There are two ways of mining: open pit, where the top layer of soil is removed and the ore is pulled out by excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. And there's also the in-situ leaching method. Pipes are driven into the ground, and special solutions are pumped in to wash out the uranium directly from the rock, and then it's pumped back out. All this ore, a grayish-brown rock, looks no different from ordinary stones. But in it, uranium-235 is only 0.7%. The rest is almost useless mass that doesn't work in a reactor. And to squeeze the needed drop of energy from it, you have to process hundreds of tons. That's why they say nuclear energy is quite a marathon. After mining, the ore is crushed, ground, and thrown into a chemical bath. Acid or alkaline solutions are added to extract the uranium, like coffee from a filter. Then, filtration, precipitation, drying at 500 degrees Fahrenheit. And at the output, yellowcake, a yellow, powdery concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks beautiful, mustard-colored, fluffy, like a spicy powder for barbecue. But God forbid you inhale or touch it. Alpha radiation, a long half-life, dangerous dust that penetrates the lungs and settles there forever. People work with it only in respirators, suits, behind 3 layers of glass protection. Yellowcake is packed into double-walled barrels, loaded onto trailers with an escort, and wrapped with radiation signs. And off it goes to the enrichment plant. It's from this poisonous dust that the journey begins, leading to the white light of a lamp over a kitchen table, or the electricity in the subway rushing under New York. Well then, yellowcake is here, in barrels, radioactive and dry as a desert wind. The next step, turning it into a gas. And not just any lavender-scented gas, but uranium hexafluoride, the very same from which the required isotope for reactors and more is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, and converted into uranium dioxide. And here the magic begins. Uranium dioxide is treated with fluorine in special reactors at a temperature of 1000 degrees Fahrenheit. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees Fahrenheit. That is, you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It is extremely toxic. It corrodes metals, destroys skin, and in humid air, it immediately turns into hydrogen fluoride and uranic acid. That is, a deadly cocktail. That's why all this is done in sealed, automated reactors that look more like devices from a villain's laboratory. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, monitoring the sensors. Any mistake, boom, or hiss, and you're already in a hazmat suit, scratching your heels on the way to the shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, barrels with engravings, a batch number, and a radioactive sign. Each one weighs under 14 tons. And so, mission accomplished. The dust is turned into gas, ready for the most interesting part: isotope enrichment. But don't rush to celebrate. This gas is like a wild cobra. beautiful, shiny, but if it bites, no one can save you. You think spinning a washing machine is fast? You haven't seen nuclear centrifuges that do 70,000 revolutions per minute. That's 10 times faster than an airplane turbine. And all for one thing, to separate uranium isotopes. The fluorine-enriched uranium dioxide, that same poisonous gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms fly to the edge, while the lighter U-235 atoms stay closer to the center. A tiny, microscopic difference, 1% in mass, and all this explosive technology spins just for it. But one centrifuge is not enough, so they are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so cycle after cycle, until the U-235 content becomes at least 3 or 5%. This is the reactor standard. For weapons, of course, completely different routes are taken. They are classified and under strict international control. Okay, the gas is enriched, but in its gaseous state, it won't feed a reactor. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under a pressure of 20 tons into small cylindrical pellets with a diameter of 3/10 of an inch. They look almost cute. But each such pill is like a charge of energy equivalent to 17,000 cubic feet of natural gas. Next, the pellets are sintered in furnaces at almost 3,000 degrees Fahrenheit to make them strong, like porcelain. Then they are polished, ground. Perfect dimensions are important for a tight fit in the cladding. The pellets are placed in long metal tubes, fuel rods, usually made of a zirconium alloy, because it doesn't rust, doesn't react with water, and withstands insane radiation. Over 300 pellets are placed in each rod. The rods are hermetically welded and combined into modules, fuel assemblies. They look like a frame of several dozen tubes, assembled in a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly, testing for leaks, uniformity of filling, weld integrity, behavior under temperature. There are no trifles, because each of them can cost not just money, but lives. The finished fuel is packed in armored containers that can withstand impacts, fire, and falls from a height. Transportation is under guard on a special route with an escort, GPS, and mandatory. 2 seals, 3 codes, and a dosimeter on each side. Because even in its peaceful form, this is a dangerous thing that commands respect. After all this, what remains is depleted uranium hexafluoride. They call it tails. It's a mixture of isotopes where there's still a bit of uranium-235, but not much. These tails are stored in steel drums on special sites under supervision. But in the future, they can be reprocessed in new generation reactors, where everything will be squeezed out to the last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It is removed, carefully, with a robotic system, and moved to pools of water. The depth is over 20 feet. The water cools and shields the radiation because the fuel is still hot, physically and radioactively. There it rests for several years. Then, 2 paths, either long-term dry storage in concrete containers with double walls, or reprocessing. In other countries, because the US mostly stores rather than reprocesses. In dry storage, the cassettes stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This is not the end, but a new stage of life. Slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water, or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand-woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution, and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Did you know that the machines powering global industry, transportation, and our electrical grids consume energy equivalent to building thousands of the Great Pyramids of Giza every single day? This hidden power isn't just about raw force. It's delivered by some of the most massive and awe-inspiring engines ever conceived. From the dawn of the industrial age to today's modern world, engineers have chased the dream of bigger, stronger, more efficient powerhouses. Get ready to take a journey through history and dive into the incredible scale and engineering genius behind the world's most powerful and giant engines. Our journey begins in the age of steam, a time when raw pressure was king. Picture the late 18th and 19th centuries. The engines that drove the Industrial Revolution weren't small. Early steam engines were clunky, but they quickly grew into colossal machines. Think of the beam engines, towering structures in factories and mines, with massive beams rocking back and forth, driving pumps and machinery with the power of boiling water. These were mechanical giants, their sheer physical size necessary to contain the immense forces of steam pressure. As steam technology evolved, so did the engine's power and scale. Reciprocating steam engines became the heartbeat of global shipping. Imagine the engine room of a massive early 20th century ocean liner. You'd see multi-cylinder engines with pistons the size of trash cans, connecting rods like tree trunks, and crankshafts so large they needed multiple men just to inspect them. These engines were colossal, spanning multiple decks. They're rhythmic pounding driving propellers, powerful enough to push thousands of tons across vast oceans. They were engineering marvels of immense moving parts, powered by the simple expansion of steam. While steam dominated for a long time, the early 20th century saw the rise of a new kind of giant, the diesel engine. Unlike external combustion steam engines, diesels burn fuel directly inside the cylinder. This was a game changer for efficiency and power density. Early large diesels quickly found their way into ships and power generation. Imagine a large, slow-speed marine diesel engine built for a cargo ship. These engines are absolutely colossal, often standing as tall as a multi-story building and stretching the length of a gymnasium. Modern marine diesel engines, like some built by Wärtsilä or MAN, are among the largest machines on Earth. The biggest ones have multiple cylinders, each with a bore, diameter. Wider than a grown man is tall. Their crankshafts are multi-piece monsters, weighing hundreds of tons. These engines produce over 100,000 horsepower, enough to move supertankers and container ships carrying 20,000 containers. The sheer scale of these components, pistons, connecting rods, crankshafts, cylinder blocks, is mind-blowing, a testament to achieving immense power and torque from internal combustion. As technology advanced further, especially in the mid-20th century, the gas turbine emerged as another powerhouse. Unlike diesels or steam engines that use pistons, gas turbines burn fuel to create hot gas that spins a turbine wheel, similar to a jet engine. While aircraft engines are built for power to weight, industrial and power generation gas turbines are built for sheer output. Imagine a power plant gas turbine the size of a bus or even a small house. Modern industrial gas turbines, like those in GE's H-class, are engineering marvels generating hundreds of thousands of kilowatts, enough electricity for hundreds of thousands of homes from a single unit. They involve incredibly complex internal components, spinning at thousands of revolutions per minute in temperatures hotter than molten lava. Their power output, efficiency, and relative compactness compared to older technologies make them the giants of modern electrical generation. Some large ships, including cruise liners, also use gas turbines for their combination of power and smoother operation. Comparing these generations of giants is fascinating. Steam engines were the pioneers, relying on brute pressure and massive physical structures. Diesel engines brought efficiency and incredible low-end torque, dominating heavy transport. Gas turbines delivered immense power density and high-speed rotation, becoming the backbone of modern power grids and high-speed applications. Each technology pushed the boundaries of materials, science, and engineering to harness energy on an ever-increasing scale. These engines, whether the visible, rhythmic giants of the steam age or the humming complex powerhouses of today, are the unseen heart of the modern world. They drive global trade across oceans, power the trains that move goods and people, generate the electricity that lights our cities and runs our factories, and fuel the massive pumps and machinery of heavy industry. They are a testament to humanity's relentless drive to build bigger, stronger, and more powerful machines. So, the next time you see a massive cargo ship, a powerful train, or simply flip a light switch, take a moment to remember the incredible journey through history and the engineering genius behind the world's most powerful and giant engines. From towering steam engines and colossal marine diesels to blazing hot gas turbines, they are the hidden giants that built our modern world. What era or type of giant engine fascinates you the most? Let us know in the comments. Hey, pull that bottle out of your pantry. Sunflower oil. You see it every time you cook, right? It's just oil. Looks simple. Pour it, heat it, done. But what if I told you that this everyday kitchen staple starts as tiny black seeds and goes through a massive, mind-blowing industrial journey? We're talking about a process of incredible scale, precision engineering, and turning millions of tons of seeds into that clear liquid. Forget your garden patch. Get ready to see the hidden factory secrets behind pure cooking oil. It all begins in the sun-drenched giants of the plant world. Sunflowers. Picture fields that stretch beyond the horizon. Golden faces tracking the sun. These aren't grown just for beauty. They're an industrial crop, covering massive hectares in places like the American Midwest, Eastern Europe, and South America. Contract farmers cultivate them specifically for oil content. When the heavy heads hang low, packed with seeds, specialized harvesters sweep through. These machines are beasts. They rip off the heads, shaking and collecting tons upon tons of seeds in hours. Enough seeds from just one field could fill dozens of semi-trucks. It's harvesting on an epic scale. Once those trucks dump their colossal loads at the processing plant, the real industrial ballet begins. First challenge, cleaning. Seeds from the field come with all sorts of hitchhikers. Dirt, stones, stems, leaves, even metal bits. Contaminants can damage machinery and ruin entire batches of oil. So, the seeds hit a high-speed cleaning gauntlet. They pass over vibrating screens that filter debris, under powerful magnets that yank out metal, and through air classifiers that blow away lighter impurities. The most impressive tech? Optical sorters. Cameras scan every single seed flying by on a conveyor, using light and imaging to spot defects or foreign objects. Precise air jets blast away anything that doesn't belong. They clean millions of seeds per hour, ensuring only pure seeds move forward. This is factory efficiency in action. Clean seeds still have their shells, and the oil is hidden inside the kernel. Next up, hulling. Machines use impact or friction, think high-speed centrifuges or rollers, to crack the tough outer hulls without smashing the valuable kernels inside. It's a delicate balance of force and precision. Then, incredibly clever systems use gravity and air currents to separate the lightweight hulls from the heavier kernels. The hulls aren't wasted. They're often used as fuel for the plant's boilers or processed into animal feed. Maximizing yield means using every part of the seed. Now for the main event, getting that oil out. There are usually two methods. First, mechanical pressing. The kernels are fed into massive screw presses. These are industrial powerhouses. They twist and compress the seeds with enormous force. We're talking pressure equivalent to stacking several elephants on a single spot. Under this immense pressure, the crude oil is literally squeezed out. It flows out in a thick, brownish-yellow stream. This first press extracts a significant portion of the oil, leaving behind a compressed cake of seed material. To extract the maximum amount of oil, especially from the leftover seed cake, a second method is common: solvent extraction. Yes, solvent might sound chemical, but it's a food-grade process, and the solvent is completely removed later. The compressed cake is washed with a specific solvent, like hexane, which dissolves fats. Think of it like a supermagnet pulling out the oil remaining in the material. The mixture of oil and solvent is then heated. The solvent evaporates quickly and is captured for reuse, leaving behind the crude oil. This process gets virtually every drop of oil possible, maximizing efficiency on an industrial scale. After pressing and extraction, you have crude sunflower oil. But it's not the clear, neutral oil you pour in your pan. It's cloudy, has a strong odor, and might contain trace impurities. So, it undergoes refining, a multi-step purification ballet. Degumming removes sticky phosphorus compounds. Bleaching uses natural clays to absorb pigments and make the oil lighter. Then comes deodorization, perhaps the most critical step for a cooking oil. Steam is passed through the hot oil under vacuum, stripping away compounds that cause smells and unwanted flavors. This is what gives the oil its pure, neutral taste and makes it stable, so it doesn't go rancid quickly. The final steps ensure maximum purity and quality. The refined oil goes through polishing filters to remove any last tiny particles, making it perfectly clear. Then, rigorous quality control takes over. Labs at the factory test every single batch. They check for clarity, color, free fatty acids, peroxide value to measure oxidation, and overall stability. This isn't a quick check. It's precise chemical analysis, ensuring the oil meets strict global standards for food safety and quality. Only batches that pass this final gauntlet are approved for packaging. Packaging is the high-speed finale. The pure, refined oil flows to the bottling lines. Empty plastic bottles or glass jars zip along conveyors at incredible speed. They're rapidly filled with precise amounts of oil, capped, sealed, and labeled by automated machines in a blur of motion. A large plant can bottle tens of thousands of units per hour. These finished bottles are automatically packed into boxes, stacked onto pallets by robotic arms, and readied for distribution. From a vast field of seeds to perfectly sealed bottles, it's a journey of transformation driven by engineering and scale. So, the next time you pour that clear, pure sunflower oil, take a moment to think about the complex industrial magic that happened behind the scenes. From countless tiny seeds, through powerful presses, intricate cleaning systems, chemical purification, and high-speed bottling lines, it's a product of massive scale, precision, and technology. It's a fascinating look at how agriculture meets industrial engineering to create something essential for everyday life. What part of this incredible process surprised you the most? Let us know in the comments.